Hello and welcome to the Cyber One YouTube channel. My name is Fred and this video is an introduction to PID Control Systems. Over many years, people have tried to come up with ways to regulate flow, temperature or speed based on what's happening in the real world. An example would be a hydroelectric power generator. When there is not much load on the generator, you need the water supply valve closed down a lot. As the load is added to the generator, it will start to slow down and the voltage drop unless we open the water supply valve more. In this case, the speed of the generator is inversely proportional to the load and proportional to how much the water supply valve is open. One method to regulate this water flow was a collection of methods known as the PID control. PID stand for proportional, integral and derivative, the three methods used in PID control. This system has become so popular it's now used in heating, speed, flow and even positioning control systems. This video I'll explain how the PID works and go over how to tune a PID loop. Let's get started. Let's get a few terms out of the way. Target value. This is where we want outflow, position or speed to be at. Current value. Where our current position, speed or flow is. Error value. Error value is the difference between the target value and the current value. Constant. This is a value that does not change once the system is put into service. It is common practice to label a constant with the uppercase letter K and suffix the K with the lowercase letter representing the constant function, e.g. Kp, Ki, Kd. Output value. This is the output signal that is used to control the valve, motor or power level. In a PID loop there are four output values. The main output value is the sum of the other output values. Now that we have those terms defined, let's look at the three individual equations that make up the PID loop. Proportional control, integral control and derivative control. Proportional control. As the name suggests, proportional control systems will take the error value and multiply it with a constant known as the proportional constant Kp. The problem here is if the constant is not high enough, then the output will not drive the system hard enough to reach the target value. It will always fall short. If we set the constant too high, then it will always overshoot the target value, resulting in oscillations and instability. Even with the proportional constant at its most optimal setting, the current value will get close, but never settle at the target value. Integral control. To try and remove the shortfall issues associated with the proportional control equation, the integral equation was created. This equation tries to compensate for the continuous error value by compounding the error value over time. Does this by using an initialized variable and adding the amount of the error value multiplied by the time between loops to it, each time the loop is executed. The integral value is then multiplied by the integral constant Ki. There is a downside to this control. In a slow-acting system, the integral value can build up to a very large value resulting in overshoot. Once the error value is negative, or overshot the target, the integral value will start to reduce, but this is a time-dependent value and will take time to reduce. The result on a well-tuned system is an oscillation that is reducing, what is commonly known as ring down. Derivative control. To try and overcome the ringing effect caused by the integral component, the derivative function serves to dampen the speed of change of the error value. The derivative is the difference between the last error value and the current error value divided by the time between the loops. The output is the derivative value multiplied by the derivative constant Kd. This has the effect of slowing down any change in the rate of change in the error value. This part of the equation on its own will never bring the current value to match the target value, but serves to dampen the rate of change, helping to dampen the oscillations that can be introduced in the previous two equations. Putting it all together. The PID loop is the sum of each of the above equations, working together to get the current value as close as possible to the target value. It is not uncommon for one or two of the settings to be set to 0.0, resulting in a P loop, PI loop, I loop, or even an ID loop. Tuning a PID has been considered by some in industry as being more of a dark art than science. This tends to be more from people who do not understand how a PID loop works. Tuning it up. Secret to tuning a PID loop is by starting with the proportional part first. Gradually increase the value of the Kp until you start to get oscillations, then back it off a bit so as to stop the oscillations. When set correctly, the current value will be close to the target value but will have fallen a bit short. Next, add a small amount of Ki. Take this setting slowly, as large values will cause the system to become unstable very quickly. The higher you set this value, the more the current value will oscillate. Good setting will see the oscillations ring down over a short period. Finally, set a small value to the Kd value. This will dampen the rate of change in the current value. Too large a value here will slow down the rate at which the PID loop will reach and settle on the target value, or even prevent it from settling down altogether. External factors that affect a PID loop. The rate at which a PID loop run, or the rate at which an output value is implemented in the field, can vary greatly. For example, if you have a motor-driven valve and want to control the flow rate of water through that valve, there may be some delay between the output command from the PID loop and the valve being set at the requested position. In this case, a large Ki value will become very unstable very quickly. Here is an example of some program code. If you like this video, then please click on the like button. You may even want to subscribe and click on the notification bell to be notified when more videos like this one are released. If you have any questions, then please leave a comment below. All of this costs you no money and helps us to create more content like this video. If you would like to help the channel out further, then please consider becoming a Patreon. There will be a link in the description. We look forward to seeing you in the next video.